Okay, so hello and welcome everyone to week one of interactive live sessions for the course called The Fundamentals of Convective Heat Transfer. Uh, the course is being instructed by Professor Amaresh Dalal from Department of Mechanical Engineering, IIT Guwahati, and I'm a PhD scholar at IIT Madras. My name is Debjit, and we will be solving problems and discussing the course material together. And let's try to keep these sessions as interactive as possible. And whatever doubts, whatever questions you may have related to the course material, you can just ask away. The course lectures themselves are one-sided. Nothing else to say. But as far as our interactions are considered, let's keep them as much a two-way thing as possible. Okay. With that, let us begin. We will move on to question number one of today's session. Uh, Let me tell you the ground rules first. I will be sharing these questions. You will read them up correctly. Then try to pick the correct answer over here, and I will be sharing a poll as well in Google Meet. You can select the correct option of the poll from there, and after that we will discuss the solution of the questions and how to arrive at those solutions. Is that clear? With that, let us begin. So question number one says, select the correct definition of convection. There are three options given, and you have to pick out the correct definition from there. So option A says heat transfer by bulk movement of molecules within fluids. Option B says heat transfer by microscopic collisions of the particles and movement of free electrons within a body. And option C says heat transfer through electromagnetic radiation. Now, I will be sharing the poll. The poll is currently live. Once you have read the question properly and arrived at the correct solution, you can put in your response in the poll. If you are having any problems accessing the polls, you can unmute and say that. We will try to figure that out. Sometimes when using a mobile phone to do that, there are some problems. Yes,
Yes, sir. I'm using my mobile phone and I am unable to access poll.
okay. So in your mobile, on the top right corner, you see a icon for options. It's usually three dots, I guess. So if you pick that, uh, I'm sure you'll be able
So,
to see activities.
yes, sir.
Yeah,
Yes, sir.
and under activities, the poll would be there. You will be able to uh, access that, I'm sure.
So after clicking on activity, sir, there is no. Yes, sir. Yes, sir.
Okay,
I am able to access now. Okay.
great. So I'll read out the question once again. The question says, select the correct definition of convection. So as we know, this course is for fundamentals of convective heat transfer. So this is the main fundamental thing which we will be looking at in detail. But first things first, what is the correct definition of convection? Is it heat transfer by bulk movement of molecules within fluids? Is it heat transfer by microscopic collisions of particles and movement of free electrons within a body? Or is it heat transfer through electromagnetic radiation?
Sir, there is a difficulty for accessing the poll.
What is the problem now? You have arrived at the location where poll is available, right? After that,
Yes, sir. I'm clicking on poll. There is a message one active, but when I
yes.
am clicking on, so no further
Uh,
means.
I'm not sure how to resolve that. Can you click on that location where one active is being shown?
Yes, sir, but no selection for the further process.
selection for the further process. The poll is live as far as I can see. What about other participants? Is everyone able to access? I am not seeing any responses. So I'm not sure. What about the others? Anyway, let's forget about polls. You can put in your response in the chat box as well. Okay, so you are able to access the polls, right? I can see 2 votes in favor of option A. So I'll assume that you are being able to access the poll. Great.
Uh, yes, sir. I am able to access the poll.
Okay.
Myself, Digandhar. Yeah.
Yeah. Hello. So okay, amazing. So both responses were in favor of option A, and if you look at the correct solution, the correct answer is also option A. So that's well done, you guys. So heat transfer by bulk movement of fluid is exactly the way we define convection. The other two options, option B, heat transfer by microscopic collisions of particles and movement of free electrons. That's the definition of what? Can anyone say? You can unmute and answer.
Sir, that is for conduction.
Correct. And what about the last option, option C, heat transfer through electromagnetic radiation?
So that is for radiation.
Exactly. So the answer lies within the option itself. So heat radiation is heat transfer through electromagnetic radiation. That's why it's called radiation. So these are the three different manners in which heat can be transferred between 2 points, let's say point A and B. And for the entire course, our main focus will be on convection only. But from time to time, we will definitely be needing conduction and radiation as well, since the broader topic is heat transfer. So we will never lose sight of them, so to say. Okay, so amazing. Let's move on. So we will move on to question number 2 of today's session. Question number 2 says that the gradient of v equal to 0, this equation can be determined as the continuity equation under which conditions. So there are, so this equation that del dot v equal to 0, uh, this is a form of continuity equation but under certain specific conditions. So what kind of conditions are they? So if we look at the options, option A says steady incompressible flows, option B says unsteady incompressible flows, option C says both A and B, and option D is none of the above. So try to read this question carefully, and once again I'll launch the poll. So once you have figured out the correct answer, you can select the option within the poll. Okay, so quick responses, all in favor of option A once again. But if we look at the solution, it's not only option A, it's true for option B as well. So let me try to explain this a bit. So the thing is, if we take a look at, uh, continuity equation in general, so that is dou t of uh, dou t of rho. Okay, admit. Okay. Rho t of rho plus dou x of say rho u and so on. This will be same for the ui as well, and same for z direction as well. I'm not writing that equal to 0. So in if it's an incompressible flow, regardless of being steady or not, this would turn out to be 0, and this would boil down to the grad of v, del dot b. So this equal to 0. So this is true not only for steady cases, it's true for unsteady cases as well, because the density at a point that is remaining constant with time. Okay, does that clear things up?
Yes, sir.
Okay. So we will move on to the next question. At any point, if you have any doubt, please stop me and ask. Okay. So moving on to question number 3. Question number 3 says Nusselt number. This can be thought of which of the following? There are four options. Option A says dimensionless heat transfer coefficient. Option B says dimensionless temperature gradient. Sorry, one second. Option C says ratio of convective heat transfer to the conductive heat transfer. And option D, all of the above. So it's basically regarding the definition and the different ways in which we can think of Nusselt number. Take a look at the options and pick out which one or which ones are correct. The poll is live, and once you have figured out the correct option, you can cast your vote within the poll. So I'll read out the question once again. Nusselt number. Nusselt number is a very important non-dimensional number which will show up in this course again and again. So what can it be thought of? There are four options: dimensionless heat transfer coefficient. Option B, dimensionless temperature gradient. Option C, ratio of convective heat transfer to conductive heat transfer. And option D, all of the above. So which one will it be? I can see one response within the poll. Yeah.
Sir, can I tell directly?
Uh, that would be disturbing once more people join this. You can either access the poll and put in your response over there, or if that is being problematic, then you can type in the chat box. That also works.
Okay,
Okay,
okay sir. Okay.
thanks. Sir, can you please mute yourself? You are still on unmute. Okay, thanks. Okay, so we have received a few responses and they are in favor of option C. I'll end the poll, and if we look at the correct answer is not option C but rather option D, that is all of the above. So why is that? We will go from option to option. Let's say the first one, dimensionless temperature gradient, dimensionless heat transfer coefficient. That is true. Why? Because if we look at, first of all, if we look at the definition of Nusselt number mathematically, that is HL by K, where H is the dimensional heat transfer coefficient for convection, and one second. Okay, so H is the dimensional convective heat transfer coefficient, K is the conductivity, and L is the length scale of whatever problem that we are considering. So this is how Nusselt number is mathematically expressed, and as we can see that this H is a dimensional quantity, but once it is expressed this way, this Nusselt number, this becomes a non-dimensional number. And in a way, Nusselt number is the non-dimensional heat transfer coefficient. That's why option A is correct. And if we take a look at option B, dimensionless temperature gradient. So if the temperature gradient is not only temperature gradient, all the important parameters are non-dimensionalized as such. Let's say T at certain x minus, sorry, if we try to non-dimensionalize the temperature in this way, and we non-dimensionalize the length scale as well in this way, then we can see that if we properly solve it, it was shown in the slides in the lecture, we can see that this Nusselt number, this boils down to the non-dimensional form of the temperature gradient as well. So that is why option B is also correct. And option C, the ratio of convective heat transfer to conductive heat transfer. So this also, if we look at, let's say if we take a case, and what is the heat transfer by convection? That can be written as HA into delta T. And if we look at the heat transfer by conduction through that same film of liquid in which convection is being considered, then that would boil down to something like this. And if we solve this out, if we delete the the common parameters in the numerator and the denominator, then we will reach the expression which we found out here. And we can see that this, what we started out with, this was the heat transfer by convection, and the heat transfer by conduction, the ratio of that is nothing but the Nusselt number. So that is why option C is correct as well. As a result, all of the above options A, B and C are correct when it comes to how we can think of Nusselt number. It can be thought of in different ways. I hope that clears things up. If there are any doubts, you can ask. Any questions? So if not, I'll hope that everything is clear and we will move on. So moving on to question number 4. This is related to the topics where convection becomes relevant. So select the topics in which convective, oh, I'm so sorry. I'll correct this one. In which convective heat transfer is of relevance. Okay, I'm sorry for that. So this is question number 4 for today's session, and it says that select the topics in which convective heat transfer is of relevance. Is it option A, electronics cooling? Is it option B, refrigeration and air conditioning? Is it option C, industrial power generation? Or is it D, all of the above? Once again, the poll is live. Once you have read the question carefully and figured out the correct solution, you can put in your response in the poll. We have received one quick response in the poll and a very quick response in the chat as well. I'm hoping for others to join in as well. And meanwhile, if there are any questions, doubts, anything, please do not hesitate. Just unmute and ask. Okay, so we have received some responses and all in favor of option D, all of the above, which is indeed correct. I'm sure this does not require much discussion. So everyone is convinced that when it comes to electronics cooling, it's a very hot topic these days, because the electronic chips, they are getting smaller and smaller day by day, and a lot of resistors and transistors, they are being packed within that compact chip, and as a result a lot of current flows through it and a lot of heat is being generated. But that heat, if it remains unchecked, if it's not transferred away from that, that can cause the chip to get heated up and ultimately damage the components. So that's why convective heat transfer is of very high relevance there. And option B, refrigeration and air conditioning. Of course, the main purpose of refrigeration or air conditioning is to cool the air, and air is a fluid. To cool that itself requires a good understanding of convective heat transfer. And apart from that, the components within a refrigeration or air conditioning system, like the compressor, the evaporator and all that, over there also a good understanding of convective heat transfer is extremely important. last but not the least, industrial power generation. Any let's say thermal power plant is is grounded. It has a strong footing within very good understanding of convective heat transfer. Okay, so I hope that clears things up. We will, if there are no questions, we will keep moving on. We'll move on to question number 5, which says match the following. It's a very simple one. There are two columns. The first column has only two options: conductivity K and convective heat transfer coefficient H. And on the right hand side, there are several units. Option 1 is watt per meter square, option 2 is watt per meter Kelvin, option 3 watt per meter square Kelvin, and option 4 watt per meter. So what you have to do is match the following. Let's say there are two options given in the first column. You have to pick the correct unit of that particular physical quantity, and that's how you will end up getting the correct matching. And once you have figured out that, you can select the correct answer, select the correct option from the poll. The poll is live. Once you have figured out the correct solution, you can cast your vote over there. Okay, so very quick responses, most of them in favor of option D. So we will have a look at the solution. The solution is that option D is indeed the correct solution. So we are ending the poll, and if we briefly discuss this, we will first consider conductivity K, and if we look at the definition, look at not the definition, so to say, the way in which K can be used. Let's say Q equal to Ka by L into delta T, and if we try to figure out the units from there, Q has a unit of watts, and this would be equal to K in a meter square. We will keep K as it is, meter square, by length can be expressed in meters, and temperature difference is in Kelvin. So meter cancels out, and now if we look at the unit of K, that is uh, watt per meter Kelvin. So A would be, A would consider to option 2 from the second column, and if we look at heat transfer coefficient H, then also we can see that Q can be written as H A into delta T, and using a similar thing, watt equal to H, meter square, and Kelvin. So from here we can say that the unit of H should be watt per meter square Kelvin. So B would correspond to option 3 in the second column. So this A2 and B3 would be the correct solution. So option D is the correct one. So I hope that's clear. I can see a question in the chat box. Hello, do we have session today? Yes, Arun, we are having a live session today, and every week we will be having these live sessions on Tuesdays from 6 to 7. That's the slot. Please try to join every week. Okay, so any questions so far? Feel free to unmute and ask. Please don't hesitate, because these are interactive sessions and we will try to maximize interactions as much as possible.
Debjit sir, can you go to the question 1 and 2? Just actually, I have joined late. I want to note the questions.
It would be difficult to go back again and again.
Okay.
These videos will be are being recorded and they will be uploaded, and the links will be made available to you. You can
Okay,
always
fine.
go back and
Fine.
check.
Thank you.
And in the end, if we have time, we will definitely go back to questions 1 and 2.
Okay, okay, sir. Fine.
Okay, thanks. Okay, so if there are no further questions, we will move on to question number 6. This is a numerical, and I'm expecting you to pull out your pen and paper and try to solve this one. You'll be hopefully needing a calculator as well. So this is how the question goes. So consider the figure shown below. There is a figure of a slab having a temperature difference across it. There is a higher temperature T1 in one end and a temperature T2 in the colder end. The area of the wall is given by capital A and the length is given by capital L. Those data are also given. So let's go back to the question. So given that there is a heat flux of 80 watt per meter square, so we know the heat flux going through it, flowing through the slab, and T2 is 300 Kelvin. We know T2 as well. So knowing all this, and dimensions of the slab are as follows: L equal to 0.5 meters and A is equal to 1 meter square. Also, the thermal conductivity K is given, that is 0.8 watts per meter Kelvin. This is roughly the thermal conductivity of concrete. So we can think of this as an actual wall. So given all this, we have to find out T1. I launched the poll, but I would request all of you to take time and solve this one, and then once you have landed into the correct option, put in that as a response in the poll.
I have given the answer in chat box, sir.
Okay. For others, I would request you to not look at the chat box and try to solve it yourself. It's a simple one. No need to worry about it. But actually solving it would ultimately benefit you. Okay. So all the responses and all in favor of option C, that is 350, and it's indeed correct. I will just quickly show the working so that everyone can agree over here. So a very simple Q equal to K A by L into T1 minus T2. We know everything except T1. So if we rearrange this equation, it would boil down to T1 equal to T2 plus QL by KA. And if we plug in the values over here, T2 we know to be 300, Q is given as 80, L is zero point 0.5, K is 0.8, and A is equal to 1. So no need to worry about that. So if we take this out and A divided by 80, this would be 100, and 100 into 0.5 would be 50. So 300 plus 50, 350. Simple. So I hope there are no questions regarding this. Anyone having any doubt? No. Okay. This is a very simple one. Let's move on. We'll move on to question number 7 of today. So select the law that determines the radiative heat flux for a body. Is it option A, Stefan-Boltzmann law? Is it option B, Planck's law? Is it option C, Kirchhoff's law? Or is it D, Wien's displacement law? Okay, so all answers in favor of option A. I'm ending the poll assuming everyone has answered, and it is indeed Stefan-Boltzmann law. So how do we write Stefan-Boltzmann law? We can write Q equal to emissivity, then the Stefan-Boltzmann constant into whatever the temperature in which the body is in. Sorry, so T1 to the power 4. minus T ambient to the power 4. So this is the net heat flux due to radiation. If we look at only radiation emitted from the body, then it would be epsilon sigma T1 to the power 4. And if you look at only the irradiation, the incoming radiation, then that would be same thing for T infinity to the power 4. And if we look at the net exchange of heat through radiation, then it would be T1 to the power 4 minus T infinity to the power 4. Pretty simple thing. I hope there are no doubts. If not, we will move on. We'll move on to question number 8 of today. So here we can see there are two figures given, and each of the figures, they represent a certain flow regime, and from that you have to identify which one represents an external flow and which one an internal flow. This identification, although may seem trivial, but for solving problems in real engineering situations, a good understanding and identification of this is the first step to it. And as far as details of convective heat transfer are considered, they treat internal flows and external flows differently. We will see this as this course progresses and we dive more into the details of it. But as a initial thing, identification is important, and everyone has responded in favor of option B, and option B is indeed the correct one. So if you look at the first figure, it shows a sphere or a cylinder above which around which there is a flow, and the main way in which to identify is that the far field goes off to infinity and we don't worry much about it. What we're worried about is only the what happens within the vicinity of that body. So that's why that's an external flow, external to the body. And if we look at figure 2, we can see that there is a confinement. There is a duct within which fluid is flowing. So over here we are worried about what is happening within the confinement. So that's why that's an internal flow. Okay, so very simple stuff, but important nonetheless. I hope there are no questions. If there are, you can always unmute and ask. Okay, so if there are no questions, we will move on to question number 9 of today's.
Debjit sir.
Yes, sir.
Sir, I have a question. Now, for example, duct is there, and inside the duct, for example, a hollow cylinder is there, or maybe cylinder is there,
Okay.
and the flow is taking place through that duct and on that cylinder. Now, it is a combination of internal flow as well as external flow.
Correct.
Okay.
So this is a situation you're talking about, right? Let me draw a quick schematic of it. There is a conduit like this, and we have a certain whatever, maybe parabolic, maybe plug flow kind of situation, and there is an internal body as well, which is at a different temperature, and there are interactions going on. Fluid dynamic as well as heat transfer. So yeah, correct. This is a combination of both internal and external flow, and in these situations, the main thing to consider is what is our goal over here. What is our objective? So if it's to compute what is the heat interactions of the inner body with the fluid, then of course we will treat it as an external flow, but to be kept in mind here that the far field is not that far away from it. So the walls of the conduit itself, they also interact with the fluid. So we have to make both considerations over there.
Yes.
So these are complicated situations, and it was a useful discussion. So thanks for that, and we will try to keep these things as interactive as possible. So moving on to question number 9. Okay, there is a small typo over here. Let me fix it quickly. Okay, so there are these two columns, and we have to match the types of boundary conditions along with the mathematical way in which they are expressed. So The first column has option 1 Dirichlet, option B Neumann, option 3 Robin, and option 4 Cauchy. And on the second column, we see the mathematical expressions of it. Option A says dy dx equal to f. Here we have to keep in mind that y is the dependent variable, x is the independent variable, and f, and further down in option D, f1 and f2, they are some constants or some functions. So option A is dy dx equal to f, option B is y equal to f, option C is c1y plus c2 dy dx equal to f, and option D, y equal to f1 and dy dx equal to f2. Match the following and find out the correct pairs, and once you have done that, you can select that combination from the options given below. A good understanding of the nature of boundary conditions is very important when we are trying to approach any problem, uh, and more so in convective heat transfer. That's why this is important to go through. Okay, so we have received a few responses and all are in favor of option D. So I'll end the poll and we will look at the correct solution. The correct one is, however, option B. Okay, is there any issue? C, D, 4, C, 3, D, 4, C, D, C, 4, D. Okay, so it is correct. I was, a bit skeptical about it. Anyway, we will look into it. So in Dirichlet condition, that is for one. In Dirichlet condition, what is done is usually the exact value of the dependent variable being considered is given. So that can be expressed as a constant or some function f. So that's why 1 would correspond to A. Sorry, 1 would correspond to B. 1 would correspond to B. Then moving on to the second one, the Neumann condition. In Neumann condition, the gradient of that dependent variable being considered is given. So dy dx equal to f sort of thing. So this corresponds to option A in the second column. So for 2, it would be A. Now moving on to 3, Robin boundary condition. Robin boundary condition presents a linear combination of the value as well as its gradient to be specified. So y and dy dx, this is the value and its gradient, and we will take a linear combination of it. So c1 plus c2, c1 and c2 are arbitrary constants, and this would be equal to f. So this is how Robin boundary condition is expressed. So 3 would correspond to C, and in option 4 Cauchy, in Cauchy type boundary condition, both the value as well as its gradient is somehow specified. So y equal to some function f1 as well as separately the dy dou x equal to some another function f2 is specified. So 4 would correspond to D. So 1B, 2A, 3C, 4D is the correct solution, and option B shows that correct combination. So that's why option B is the correct one. Is that okay? Any doubts regarding this? Okay, so if not, I hope everything is clear. We will move on to the last question of today's session. So you have to select the correct statements. There are 3 statements given below, and the first statement is free convection is caused due to buoyancy forces and density differences. Statement 2 says forced convection is driven by some external source, and option 3 says in general the heat transfer coefficient for free convection is higher than forced convection. So among these 3 statements, some are correct, some are incorrect. You have to first figure out which ones are correct and incorrect. and then you have to select the correct combination from the options given below. So is it option A 1 and 2 only, option B 2 and 3 only, and option C 1 and 3 only, and option D all of the above? Here I must mention that all of the above is not for options A, B and C, but for statements 1, 2 and 3. So option D means all these statements 1, 2 and 3 are correct. Okay, so we have very quick responses all in favor of option A, that is 1 and 2 only, and that is indeed the correct one. So if we discuss a little bit about it, so the first statement, free convection is caused due to buoyancy forces and density differences. This is correct. That is how free convection is done. So this is a correct statement. Option 2, forced convection is driven by some external source. This is also correct. There is some fluid flow which is being driven by some unknown external source. We don't bother about it. We bother about how that externally caused fluid flow affects heat transfer. So anyway, this statement 2 is also correct. In statement 3, the catch is that we are saying that the heat transfer coefficient, the heat transfer coefficient for free convection is higher than forced convection. That is not true. Forced convection in general is always greater than free convection. So that is why the option A 1 and 2 correct only is the correct one. Now here is a catch here. The the statement 3. This is in general, but this is not to say that there can't be an exception where the free convection is higher than a forced convection. It may so happen that the forced convection is so weak that it could be lesser than free convection in that particular case. So of course there are exceptions, but in general forced convection is higher than free convection. Okay, is there any doubts? Are there any doubts? Sorry. So if not, that's all for today. Thank you all. You have been participating with great enthusiasm. That's always great to see. And we will have sessions like this all throughout this course. Let's hope we can have more fruitful discussions just like today.
Sir, can you go to the slide 1 and 2 just
Okay,
for
yeah,
for 1 second?
of course. We have time. We will go through questions 1 and 2 once again. So this is question number 1. I'm sorry, I won't be putting up polls or anything anymore. Let's just have an open discussion about it. So this was question number 1. Select the correct definition of convection. Very simple thing. Is it option A, heat transferred by bulk movement of molecules within fluids? Option
A,
B, A.
I got A.
Absolutely. And option B and C, they are respectively the definitions
Convection and
for
radiation.
conduction and radiation. Correct.
Yes.
And question number 2 was the del dot V, grad V, can be written as the continuity equation under which conditions? Option A,
Steady
steady
and
incompressible
incompressible.
flows, unsteady incompressible flows, both A and B, or none of the above.
Only A.
No, sorry, you are incorrect over here. It would be option
Okay.
C, both A and B. Since we are considering incompressible flow, then density would be a constant, and that would be constant irrespective of the flow being steady or unsteady.
Okay.
Okay, so that's why divergence of B equal to 0. That would be the continuity equations under both conditions, steady or unsteady. Okay.
Sir, can you elaborate on divergence just in 1 minute? How we are writing divergence?
Okay, sure. Okay, so this was the equation which I wrote earlier. I won't scribble further. So if we expand the continuity equation, it boils down this way. And as you can see that if rho is constant, then this goes to 0. And if we look at the remaining part, the dou x of rho u, dou y of dou v, if we consider 3D, then there will be a dou z of rho z as well. That would be equal to 0. and since density is constant, we can take it out as some rho naught outside of this, and rho naught if we put over there, then that also cancels out. So that's why we can write that v equal to 0 would be the expression for continuity. Is that clear?
Okay. In B option, unsteady, how it becomes 0 then? Unsteady.
Yeah, then also, since we're considering incompressible flows, what happens in incompressible flow? That rho equal to rho dot. So
Yes.
rho dot is a constant with respect to time as well. So that's why this dou dot t of rho goes to 0.
Okay.
Okay.
Yes.
So
Got
this
it.
is the catch over here. So this is if we are dealing with incompressible flows, then our lives remain pretty easy. And we
Hmm.
can simply use divergence of velocity as the continuity equation.
Yes, actually, what I thought ki unsteady means again a time factor is coming into picture,
No,
and here in divergence time is not there.
no,
That's why.
not only unsteady, incompressible.
Yes.
Okay,
So because of incompressible, that d rho by dt
goes
it
to
is 0. Yes.
okay.
Okay. Thank you, sir. Thank you.
Any other questions, anyone? Okay, so if not, we will end the session today.
But this, one minute, one
Yes.
minute. Actually, these practice sessions, I have joined this NPTEL courses very first time. These practice sessions are useful only for solving the assignment, but it is as good as the preparation of our final examinations also.
I can't say because I don't know how the final examinations are carried out. Uh, my duty is to solve these
But,
questions, and these are mostly pertaining to the assignment questions, which we will uh, solve during the course.
okay. Thank you, sir. Thank you. Bye.
Great. So that brings us to the end of today's session. So we will be having similar live sessions every week from 6 to 7 every Tuesday, and your participation has been really great. So hope to see you again next week. Thanks a lot.
Thank you, sir. Thank you.